the expected value of our y sub I is just going to be equal to, I'll tell you what, it really annoys me when I run out of space. So this is going to be beta 0 plus beta 1 x1 plus beta 2 x2 plus beta p minus 1 xp minus 1. Yeah, you might, think in the educational setting, if we wanted to predict a person's college GPA, well, what we may want to do this from is may want to let B1 be the high school GPA. We may want B2 to be, their ACT or SAT. Beta 3, which actually, believe it or not, is a very good predictor of college GPA, is mother's and father's education level. So, we could come in with as many predictors as we like. So I think we looked earlier at a simple linear regression model where we would predict the miles per gallon of a car. And you might think of multiple predictors we could use there, including weight, horsepower, and, just different things. All right, gang, the parameters for these models, as you would expect, would be beta 0, beta 1, beta 2, and beta p minus 1. And the interesting part of this is our predictors can be quantitative, and or categorical. So the multiple regression model permits us to put gender, socioeconomic status, if it was categorized, political party, religious affiliation, variables like that in. Now, if we get in a situation where our categorical variable is dichotomous, zeros and ones is usually the way we code it, like gender. The technique is not that difficult. And in fact, it's very straightforward. However, if we get into a situation where we have categorical data where we have more than two subcategories, if you will, subgroups, now we get into something called dummy variables. So I'll probably illustrate that in class. So guys, the beauty of what I've tried to do so far is I've tried to set a very solid foundation using matrix methods for simple linear regression. The fact is, if we have a firm, solid foundation for simple linear regression, then multiple linear regression follows suit. For example, our response vector is still going to be like this, and our design matrix is going to look a lot like what we had before. Close this up here. And so our design matrix has, got a little bit more going on. Obviously in the simple linear regression case, the design matrix would stop right here. But in the multiple regression, we clearly have more going on. All right, gang. Another, remember the coefficient matrix. Well, it's going to look again a lot like before, except we're just going to have more betas. Our error matrix is going to look just Doug is going to look just like before. And same things apply. We want our errors to be random, and some of the errors to be 0, some of the errors squared to be a minimum. And guys, at the end of the day, we still have this driving our calculations. Now, let's see, what do we want to do? All right, what I think I want to do next is let's consider estimation of the regression coefficients. And if we have, for example, our data x1, y1, x2, y2, and let's say that we just say that we have n ordered pairs, then from a least squares perspective, we could see that we could, using a similar notation, that we could minimize and I'll tell you what I want to do. I want to change gears on you just a little bit. And I want to do that to get you familiar with both notations. So we have K predictors. And the reason is that I know what's coming up and it'll make things less messy. So guys, here if we were going to minimize Q through the least squares approach, what we would do is we would take the derivatives and we would come up with the normal equations. And so guys, if we have K predictors, then we'll have K plus 1 normal equations. Now I'm going to go to the next screen here because there's going to be a lot to write here. So, just like before, when we have a simple linear regression, I hope you know that that we would have beta 0n plus beta 1 some xi's, some y sub i's, and we would have beta 0 some xi's, beta 1 some xi squared, and this would be, of course, some xi, yi. And what we saw, I think I did this in class for you actually, is that we could look at this as a matrix. All right, and ultimately what we could do here is we could solve for the estimates by taking And I'm going through this really, really, really fast because I expect you to already know this. All right. So we saw that in class that we could we could do this. Now, guys, what I want to do obviously is I want to, extend this to a multiple regression. So now, guys, I'll slow down now. Okay, I'm writing really fast because I expect you to already know this. So, guys, what the normals are going to look like here will be beta 0 n plus beta 1 sum xi's plus dot 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 beta sub k, or p minus 1 if you prefer that, but ik equal the sum yi's. The next one will look like, just as you would expect, or I hope you would expect that. This is hard to write this small. I hope you see that's a K. See how messy it would have been if I'd stuck with p minus 1. And final. Gonna run out of space here to daggone it. Yeah, I'm trying to not let it happen, but anyway, it's going to happen. So. Okay, so yeah, I guess this is what our normals are going to look like. Now, I mean, that notation can be a little weird, especially like, well, what does this, like, I'm going to circle this right here. What does I sub 1 mean? Well, that just means that you're running through the x sub i's for the first variable. So x sub 1, 1 would represent the first piece of data from the first variable. X sub, for example, 2i would, or I'm sorry, 2, 1 would be the second piece from 1. The first variable, x sub 2, 2 would be the second piece of data from the second variable. Now, I think it's going to be worthwhile if we run through an example for two predictors. And I would really, really, really like it if, hold on, I gotta get a cup of coffee here. Oh, hopefully I'm not slurping. I think I just did. So if we have two predictors, so ultimately we're trying to go y equals beta 0 plus beta 1 x1 plus beta 2 x2. So, if we have this, first of all, what's Q going to look like? Well, we're going to try to minimize the sum of the vertical distances squared. And I'm not even going to attempt to try to draw that. And the normal equations would, of course, look like should be xi1. I'm getting sloppy here. Alright, the next one would look like, now again, let's think. I'm going to erase this. You know, we have k equal 2 predictors. So we're expecting k plus 1 normals, okay? And that's, of course, exactly what we're going to get. Alright, gang, the next one, of course, there should be no debate whatsoever what goes first. And there should be no debate what goes next, because we can use what we've hopefully learned. Daggone, I keep forgetting that x sub 1. But, you know, there could be a little bit of confusion what goes right here. Some xi, yi. And the third one, which, you know, if you, well, let's see, I forget, this could be xi2 plus beta 1, some xi2 xi1 plus beta 2 some i2 quantity squared, and of course this is going to be equal to xi2. Wait a minute, gang, don't forget this up here. This should be I1, okay? And y sub I. Okay, let's just run through an example here. And actually, I did this before, so I didn't want to waste time on doing the calculations. And all I did is just looked at just made up some data, really. It takes on no real meaning. And actually, this is something when you guys actually do teach your undergraduate statistics for the dual credit, something I'd really highly advise you not to do. I don't ever like to use data in a class of that nature that doesn't have some sort of meaning. But you know, this is more theoretical, I guess, and so it's more dull. Okay. So, guys, well, my dog's going crazy. So, what we would want to do here, I just had a horrible feeling that I'm not even recording here, am I? Yeah. Guess I am. Yeah, cool. All right, gang. So what we'll have here is, you know, what I want to do is just illustrate the normals back here and see how this all works. So, guys, the very first thing I'm going to have is, you know, beta 0 times n. And I'm just going to go ahead and cut to the chase here. And all I want to do here is create the matrix. Yeah, it's going to drive me crazy. I can't handle this. I want to create the matrix and this is going to be equal to, of course, the other matrix. And this is following exactly what we did in class. So, you know, clearly what we're going to have in this place is 5. And if we go back and look at this particular part, this is just going to be the sum of the x's for the first variable. So what I need to do here is just sum up this column. And if I've summed up that column correctly, then I'm going to have a 29 right there. The next entry, which would be right here, would of course be the sum of the x sub i's for the second variable. So gang, what I need to do here is I need to sum up this column. And I did so. And looks like that's summed up to be 100. Now, we're also going to have a 29 right here. And we're going to have a 100 right here for obvious reasons. Because, you know, we've got the same things here. Now, next thing I need to do is I'm just going to focus on these two right here. Is I need to square up the values in this case right here. Square the values for x sub 1 and of course add those. And gang, when I do that, so ultimately what I'm doing here is I'm going to take 16 plus 121 plus 225 plus 28 squared, which I don't know. But nevertheless, when I do that, I get 237. When I square up my y's, I'm sorry, when I square up my x sub 2's, no, wait a minute, I think I messed that up. I did mess that up. For this one right here, I'm taking the data in x1 and squaring those. So I would take 1 squared plus 9 plus 25 plus 81 plus 121, and I get 237 in the middle. For the bottom right, what I'm going to do is I'm going to square up the x2's, so I'm going to get 16 plus 121, and I square that up, I get 2910. I really encourage you to just check me on that. Guys, I get 826 here in both of these. And 826 is what I get by here. So ultimately what I'm doing is I'm taking the product of the corresponding x1, x2's. So it should go without saying, but you know, if I'm going to take x1, x2 and sum it up, then I'm going to take 4, 33, and so on and so forth. So I don't know. It may be worthwhile to run through that. Well, obviously, I think it is because I'm doing it. Now, what we need next is we need the other matrix. We need this information. So this is clear. I'm going to take the sum of the y's, and I took the sum of the y's and I got 625. The next thing we do is we're going to take the product of the x1's and the y's and sum those up. So back to our data set, which is the other way. I would take 1 times 100, 3 times 119. You can see we're going to get a pretty big number here. And I did this earlier and got 3,915. Guys, the other term I think is pretty clear, 13,550 is what I get when I multiply the x2's times the y's, you know, the corresponding parts, if you will. So, you know, 4 times 100, 11 times 119, and of course we add those up. Now, if I were doing this, you know, for a grade, if I were a student, you know, I would probably either in the calculator, using matrix methods, or some way, and I would go ahead and create a much neater table of numbers here. So guys, at the end of the day, we're going to see that beta 0, beta 1, beta 2 can be found by taking the product of the inverse of the first matrix times the last matrix that we created. Guys, when I do this, I end up getting 100.87, 2.68, and 0.43. So this would tell us that we would have y equals as our model. Okay? And believe it or not, it gets easier than that. Once we get into what I would call true matrix methods, where we get out of the normal equations, and I'm sure you remember this. I'll tell you what. We'll talk about this in just a second, I think. Now, so that's it. Yeah, let's do that. This would be a good time to just step back and so recall. In simple linear regression, some things that we ran into, and it's going to happen. It's going to also work for multiple linear regression. So first and foremost, what I would want you to remember is that we can calculate our coefficients by looking at the product of these matrices. Something else I would want you to remember is the standard error for the betas can be found by taking the mean square error times part of this. So it's just that part. Something else I would want you to remember is that the fitted values can be found by, we looked at it two different ways. By taking what we call the hat matrix, and I'll tell you what. Let's just don't leave any stone unturned. The hat matrix looks like this. Something else I want you to remember is the variance covariance matrix. For our residuals. Now guys, don't get this one confused with the variance covariance matrix for our coefficients B. This is the variance covariance matrix for our residuals. It's going to look like the mean square error. I forget what this is. I minus H. Yes, that's right. And again, this is the variance covariance for our residuals. Now, again, don't confuse this with the beta matrix. By the way, guys, I did this in a video kind of in passing. But remember that this matrix is going to be look like this, and ultimately it's just times identity matrix. All right. Now. Let's move our calculations into ANOVA. And again, remember in ANOVA, we're partitioning out the sum of squares. And obviously, if we can find two of them, we can find the other one by simple subtraction. So, guys, the sum of squares for the total, remember, it can be found by taking y transpose y, an easy matrix to find, minus 1 over n, y transpose j, y. And guys, remember, your J matrix is just an n by n matrix with all ones. The sum of squares for error, if my memory serves me correctly, is y transpose y, b transpose y, x transpose y. And sum of squares for the regression, again, what I would do here is I would take the sum of squares total minus the sum of squares for the error. The way I'll tell you what, let me just go ahead and be thorough here, Douglas. Transpose J, Y. Okay. All right. And just go ahead a little bit more. Now, guys, what I'm going to do in the next the next videos, I'm going to illustrate this with numbers. But remember, the mean square for regression is the sum of squares for regression divided by p minus 1, and the mean squares for the error is the sum of squares for the error divided by n minus p, where p is the number of predictors. Now, from this, what we could do is we could obviously do an f-test. I don't think I've officially stated what the f-test does. I know I have it in multiple regression. The null hypothesis just says that beta 1 equal beta 2 equal beta sub p minus 1, that all of the coefficients are equal to 0. H sub a says at least, well, I'll tell you what, let's do it this way. Not all beta sub i's are equal to 0. And of course, guys, I think it's pretty obvious here that f is equal to the mean square regression over the mean square for the error, and it follows the f distribution, degrees of freedom, p minus 1, n minus p. Now, when we want to talk about the variation explained in our from our predictors, we look at the coefficient of determination. The easiest way to look at this is the sum of squares for the regression over the sum of squares for the total. Now, this is really okay when we have one predictor. But what you can show is this thing tends to overestimate the variance that's explained in our model by our set of predictors. So you'll often see what's called an adjusted R-squared, which is much more relied on than R-squared when we have more than one predictor. If you have two predictors, there's not going to be a big difference between R-squared and the adjusted R-squared. But if you get out to a larger model where you're looking at 4 or 5, there can be a pretty big difference. So the thing I want you to know here is as the number of predictors increases, R squared tends to be kind of artificially inflated, if you will. Adjusted R squared tends to be a more stable measure. Guys, the adjusted R squared is, at the end of the day, it's just 1 minus the mean square error over the mean square total. And I hope it goes without saying, but maybe it doesn't. Remember, mean square error and mean square regression, mean square total is not additive. So we can't take our mean square error plus our mean square regression and get our mean square total. So I want to make a note of that. So mean square regression plus mean square error is not going to be equal to the mean square total as in the sum of squares. Now, sum of squares regression plus the sum of squares error is equal to our sum of squares for the total. So just put that on the back burner, all right? And probably a more commonly used, because it actually uses the degrees of freedom. Is this. So I'd probably prefer that you remember this one, because it's so tempting up here to get sloppy and have your mean square regression, mean square error, because you're going to use that in calculating your statistic. Add those two things together, get your mean square total, and you get completely the wrong adjusted R squared. And we don't want wrong answers, right? We want good answers. All right, gang, let's look at our inferences. On beta 0, beta 1, up to beta some p minus 1. And what I want you to think about here, okay, first of all, if we reject using our F statistic, if we reject that, then we're saying at the end of the day that at least one of the B sub i's is not equal to 0 and is a statistically significant predictor. Well, at this juncture of the game, what we'd want to know is, well, which one? So in this case, what we would do is we would conduct inferences on each of our betas. So, guys, don't forget, what do we need to conduct inferences? We need two parts. We need a point estimate. Well, we got that, don't we? We have a beta sub k that is a predictor. We have a b sub k that's a predictor of beta sub k, because we got that from our from the matrix operations. So, gang, we also need our standard errors, and turns out we've got it because we know the standard errors squared for our betas can be found by taking the mean square error times x transpose x quantity inverse. What we will get in this is we'll get our standard errors squared for our b's, and we'll end up getting this. So we'll get our standard error on the diagonal for B0. We'll get our standard error squared for B1. And we'll get our standard error squared for our B sub p minus 1. Now what happens here is we get our covariances. And what we get here is we'll actually get the covariance, not the covariance squared, but the covariance of b sub I, b sub j, where obviously I is not equal to j. If I was equal to j, it would be on our diagonal. So from here we can say that the standard error, for example, b sub I will be the square root of whichever one of these on the diagonal that we need the standard error for. Don't forget to take that square root, boys and girls. It's easy to do. So guys, and officially what would we do? We'd have our test statistic. Which would be equal to our b sub k minus b sub k. Guys, think of this. This is almost always 0 over the standard error for b sub k. And of course, this is for all of our k's from 0 up to p minus 1. From this, it would be easy to get a 95% confidence interval. So let's say that we are testing that b sub k equals 0. So guys, therefore, clearly our test statistic will be t equal b sub k over the standard error for b sub k. Pretend that looks like a k. And if we wanted a 95% confidence interval, we would clearly just take b sub k plus or minus the t critical for alpha divided by 2, given our degrees of freedom, times the standard error for b sub k. All right, gang, nothing new, just going over things that I hope you already know. I expect you to already know. One additional thing that I'm going to illustrate is the estimation of mean response. So first of all, we need a point estimate, which will be x sub h. I think that's the notation I used before. And it's just going to be a 1 by vector. So guys, it follows that our expected value of this will be equal to x transpose h times b. We also need the variance. Well, my pen's falling apart on me. So the variance will be this is kind of funny. I had a piece of dirt on my pen. I wondered why the pen was writing so smoothly. It had a piece of dirt on there. I took it off and now it's not writing smoothly. So guys, from a previous, we know that this is, I think it was x transpose h, x transpose x inverse times x sub h. Guys, I'll tell you what, that's everything we're going to need for the next video.